Hello friends, welcome back to my YouTube channel. So in today's video we will starting the new concept, that is Kani's method. So we'll see how to solve the problem by using Kani's method. So first we'll see the working procedure of this Kani's method. So one by one we'll see. So Kani's method, will see the procedure. First step is to find out the fixed end moment. So we already seen this method in slope deflection method as well as moment distribution method. This method is same. And second is rotational factor. So by solving I will show you how to calculate this rotation factor. Third step is to contribution method. This is also called as the rotational moment. So while analyzing I will tell you how to do this rotation moment. So and fourth step is to find out the final moment. So now we'll see one by one steps by solving the one problem. So this is our given problem. So the problem is like this: analyze the continuous beam as shown in figure by Kani's method and draw bending moment diagram. And this is our given continuous beam. For span AB, we'll solve the fixed end moment. The load is not present at the center. MF AB is equal to minus WAB square divided by L square. MF BA is equal to WA square B divided by L square. By using these two formula, we'll calculate the fixed end moment for AB as well as BA. So now MF AB is equal to minus WA into B square divided by L square. So substitute all the value. Minus load is 8 kilonewton. 8 into here, from here to here is A to here is B. So this is A and this is B. So now substitute. A is 3 meter and B is 1 meter. Minus 8 into 3 into 1 square divided by length is 4 meter. 4 square. So by simplifying it will come out as minus 1.5 kilonewton meter. Similarly we will calculate for MFBA. For that we have the formula WA square B divided by L square. So W is 8 kilonewton. 8 into A is 3 meter, B is 1 meter. A square divided by L is 4 square. By simplifying it will come out as 4.5 kilonewton. So now similarly for span BC, it is carrying the point load of 10 kilonewton. It is present at the center. For that we have the formula MFAB is equal to minus WL divided by 8 and MFBA is equal to WL divided by 8. By using these two formula we will calculate the fixed end moment for span BC. MFBC is equal to WL divided by 8. So minus load is 10 kilonewton. 10 into length is 3 meter. Length is 3 meter. 3 divided by 8. By simplifying it will come out as minus 3.75 kilonewton into meter. Now similarly for MFCB we need to calculate. For that we have the formula WL divided by 8. Load is 10, length is 3 and divided by 8 it will come out as positive 3 plus 75 kilonewton into meter. Now for span CD it is carrying the UDL of 4 kilonewton. For that we have the formula MFAB is equal to minus WL square divided by 12. MFBA is equal to WL square divided by 12. By using these two formula I will calculate the fixed end moment for MFCD. Minus WL square divided by 12. So minus load is 4 kilonewton per meter and length is 3 meter. Minus 4 into length is 3 meter. 3 square divided by 12. By simplifying it will come out as minus 3 kilonewton into meter. Similarly for MFDC we have the formula, same formula, only sign will change, here positive sign. So substitute all the value, it will come out as 3 kilonewton per meter. So our second step is to find out the rotation factor. For that we need to draw a table. It contains the first column is joints, and second is members, third is stiffness, k is denoted as k, and fourth is summation of k, and fifth is distribution factors. To find out this, we have the formula 1/3 of minus 1/3 of distribution factor. To find out the distribution factor, we have the formula k divided by summation of k. So by solving, we'll see. So this type of in moment distribution method, we have drawn the distribution factor where we have drawn this type of table. So but in our Kani's method, here rotation factor will come. Only the changes here, rotation factor we need to find out. So now we'll see joint means how many joints we have. C, we have joint B and we have joint C. So now write it here. We have joint B as well as joint C. For joint B, we have the member. Here for joint B, we have the member BA and BC. So write it here. BA and BC. And for joint C, we have the members. Here CB and CD, we have two members. For joint C, we have CB as well as CD. To find out the stiffness, here BA. So our far end is fixed, and if far end is fixed, we have the formula here for finding out the stiffness. If far end is fixed or continuous, then we need to use the k value k as I divided by L. We need to use this formula if far end is fixed. So here point A is fixed, we need to use I divided by L. So BA is equal to stiffness formula, we have to use I divided by L. So I for BA span is I for BA is 2I. So put and length is 4 meters. Substitute. I is 2I, length is 4. So by simplifying, it will come out as 0.5I. 0.5I. Similarly for BC, here for BC it is the continuing. So for continuous also we need to use the I divided by L. See, we need to use I divided by L. For BC, I divided by L is equal to, for BC, I is 3I, BC I is 3I and length is 3 meter. Put this value here. 3I divided by 3, 3 will get cancelled. Remaining is I. For CB, we have the, for CB it is continuing. It means we need to use I divided by L again. I divided by L. I is I for CB is 3I divided by 3. It means it will come same as this one. It will come 1I. For CD, again it is fixed, we need to use the I divided by L. For fixed, we need to use the I divided by L. Here 4I is there and length is 3 meters. Substitute. I divided by L is equal to 4I divided by length is 3 meter. By simplifying, it will come out as 1.33I. Now we need to summation of k. Summation of k means we need to add 0.5I plus 1I. So if we add, it will come out as 1.5I. Similarly for I plus 1.33I, it will come out as 2.33I. 2.33I. So now we'll go for the rotation factor. For that we have the formula minus half into distribution factor. To find out the distribution factor, we have the formula k divided by summation of k. So now we'll see for BA, rotation factor is equal to minus 1/2. Distribution factor formula we have k divided by summation of k. So k is 0.5I. 0.5I divided by 1.5I. So simplifying, it will come out as minus 0.166. Similarly for member BC, rotation factor is equal to minus of k is I divided by summation of k is 1.5I. By simplifying, it will come out as minus 0.333. For member CB, minus half, here also k is I divided by summation of k is 2.33I. So by simplifying, it will come out as minus 0.214. Minus 0.214. For member CD, half k is 1.33I divided by 2.33I. So by simplifying, it will come out as minus 0.285. So now we have calculated the rotation factor for these all members. Now our third step is to find out the contribution moment. It is nothing but rotation moment, it is also called as. So now we'll see how to calculate this. So for this we have to draw the diagram like this. So wherever joint is there, we need to make the boxes like this. So and here we need to write down the The first thing we need to write down all the fixed moment value. This is point A and this is B. This is C and this is D. So at point A we have the fixed moment for AB is, we got how much? So MFAB we got was minus 1.5. Write it there. MFAB we got was minus 1.5. Similarly for MFBA, how much we got? MFBA we got was 4.5. So 4.5. And MFBC, how much we got? MFBC we got was minus 3.75. Minus 3.75. And MFCB we got was 3.75. 3.75. And MFCD we got was, MFCD is minus 3 and MFDC is plus 3. So this is minus 3 and this is plus 3. So first thing we have to write down all the fixed end moment here, and in this box what we have to do is add these two and write the value here. So I will show you. See here, 4.5 minus 3.75. So I will add it. 4.5 minus 3.75. It will come out as 0.75. So write it in this box, 0.75. Similarly add these two and write the value in this box. So 3.75 minus 3. 3.75 minus 3. So it will come out as 0.75. So write it here. And here we need to find out the rotation factor value which we have got. For rotation factor for member BA we need to write here, and for member BC we need to write here, and for member CB we need to write here, for member CD we need to write here. So for BA rotation factor value we got was, for member BA we got rotation factor is minus 0.1666. So I am writing here minus 0.166. Similarly for BC we got was rotation factor value 0.333. So minus 0.333. For CB we got was minus 0.214, and for CD we got was minus 0.285. So I have written all the rotation factors value. So next, so now what we have to do is we need to find the rotation moment for member BA and BC and CB as well as CD. So for that what we have to do is we need to add minus 0.66 into 0.75 plus foreign moment value. Here 0 is there is no value. Initially we should take the 0 for foreign moment value for both the side. So minus 0.66 into 0.75, here the value is 0. So 0, here also foreign moment is 0. So if you do, I will show you. Minus 0.166 into 0.75. If you do, the value will get minus 0.124. So write it here. So minus 0.21245. Similarly for BC we need to do here minus 0.333 into 0.75. Here foreign moment is 0 and here also 0. So we need to add it. I will show here. Minus 0.333 into 0.75. If we do, we'll get minus 0.249. So write it. Minus 0.2497. Similarly for CB we need to do. So here the value is minus 0.214 into 0.75. The foreign moment for CB is here. The value which we have got, we need to add this one, minus 0.2497 plus, so foreign moment here is 0. So we need to add these three. 0.214 into 0.75. Minus the foreign moment value we got was minus 0.2497. So I add it, minus 0.2497. So now solve it. It will come out as minus 0.1070. So write it here, minus 0.1070. Similarly for CD we need to do. So for CD minus 0.285 into 0.75. Here 0 plus 0 and we need to add this value, minus 0.2497 foreign moment value. I will show. Minus 0.285 into 0.75 minus far end moment value we got was minus 0.2497. Minus 0.2497. So simplify it. It will come out as minus 0.1425. So write it here. Minus 0.1425. Similarly, we have to do for the second iteration. For BA, minus 0.166 into 0.75, and far end value is here 0, and the far end value we got was for BA. So far end value how we need to take means, see, for now we are, for example, we are calculating for BA, no? So we need to take the end moments of B. So for B is this value, far end moment. For A is far end moment is this. So now we will do the second iteration. So for member BA, minus 0.166 into 0.75. So the value we got was far end moment minus 0.1070 plus this value is 0. So now add these all. So it will come out as minus 0.1067. Similarly for BC, minus 0.333 into 0.75 minus 0.1070, and the here value is 0. So we need to add these three. So by simplifying, it will come out as minus 0.2141. So now similarly for CB, minus 0.214 into 0.75, this value minus 0.2141. So this value is, so by calculating these three, for CB, minus 0.214 into 0.75, here the value is 0, this value plus this value minus 0.2141. So by doing this, it will come out as minus 0.1146. Similarly for CD, minus 0.285 into 0.75 into this value minus 0.2141. So by adding, it will come out as minus 0.1527. Similarly for, now we need to do the second iteration. So this is the first and second. Now we need to go for the third. I will tell you when to stop later. For BA, minus 0.1666 into 0.75 minus 0.1146, and plus this value, there is no value, each value becomes 0. So we need to add these three. So by adding, it will come out as minus 0.1054. Similarly for CB, minus 0.336 into 0.75 plus this value. So it will come out as minus 0.2115. Similarly for CB, this value into this value plus this value. So if we do, it will come out as minus 0.1152. And similarly for CD, this value into this value plus this value. It will come out as minus 0.1534. Now we'll go for the fourth iteration. We have to stop when we get the value is very similar or exactly same value. When we get, we need to stop there calculating the rotation moment. So now for CB, this value into this value plus this value. So it will come out as minus 0.1053. For BC, this value into this value plus this value. It will come out as minus 0.2113. Similarly for CB, this value into this value plus this value. It will come out as minus 0.1152. Similarly for CD, this value into this value plus this value. So it will come out as minus 0.1535. So see here, our third iteration and fourth iteration, almost we got the similar value. It is very close value we got. So when we get the very close value or almost similar, see here, almost similar in third iteration as well as fourth iteration, we got the similar answer. So now we need to stop here when we get the similar answer or the value it is very close to this one. Then we need to stop calculating the rotation moment. So these all are our final rotation moment value. This is our third step. This is how we need to calculate. So I hope you all are understood. So it is very simple method. Our fourth step is to find out the final moments. So final moment, for that we have the formula MAB is equal to MFAB plus 2 into near end rotation moment plus 1 into far end rotation moment. So we'll go with a very easy method. So to find out the final moment, see here for member AB. So here first point is 1, call it as, second point is 2. So for MFO 1 2 means for AB MF AB we got the fixed end moment minus 1.5. So I have written here all the fixed end moment for corresponding member. I have written here. So now what we have to do is for AB we need to add it. So this is nothing but I have separately written this formula here. So MFAB means so I have written MF12. So MF12 means here for corresponding member we need to take the value for corresponding member of this MF12, and 2 into near and rotation moment means 2 into M dash. So our rotation moment it is denoted as M dash. 12 means we need to take the corresponding member's value, and plus 1 into far end rotation moment is nothing but M dash 21, and here M12 is nothing but we need to add these three to get the final moment. It is nothing but our final moment M12 means. So now we'll see MF12 means fixed moment we got was minus 1.5, and 2 into M dash 12 means M dash of AB. For rotation factor of AB we don't have the value for AB. We don't have the rotation value for member AB, so keep it as 0. 2 into 0, and M dash 21 means M dash of BA. So M dash of BA we have the rotation factor value for BA is so minus 0.1053. So minus 0.1053. So now add these three. So minus 1.5 minus 0.1053. So it will come out as minus 1.6053 kilonewton meter. The final moment value for AB is minus 1.6053 kilonewton meter. Similarly for member BA, fixed moment we got was 4.5. Here 2 into rotation factor of BA we got was, so BA we got was how much? Minus 0.1053. So write this value here. So minus 0.1053. Here M dash 21 means rotation factor of AB. So there is no rotation factor for AB, so keep it as 0. So now add, it will come out as 4.289 kilonewton meter. This is the final moment value for member BA. Similarly for BC, we have the rotation factor value for BC is, so BC is minus 0.2113. So add it, minus 0.2113. For M dash CB value we got was minus 0.1152. So minus 0.1152. So now add, it will come out as minus 4.287 kilonewton meter. 7 kilonewton. Similarly for CB member, fixed end moment we got was 3.75. So here we need to add these three to get this final moment. We need to add these three values. Similarly for CB, fixed end moment we got was 3.75. So 2 into rotation factor of CB we got was, for CB we got was minus 0.2113. So 2 into minus 0.2113, and rotation factor of BC we got was minus 0.2113. See here, we need to write down here rotation factor of 1 2 means CB value we need to write here, rotation factor of CB value. So rotation factor CB value is nothing but this one, minus 0.1152. So minus 0.1152, make it correct. And here rotation factor of 21 means rotation factor of BC we need to write here. So for rotation factor of BC we got was minus 0.2113. So it comes here, minus 0.2113. So now add these three. So it will come out as 3.30 kilonewton meter. Similarly for CD, fixed moment we got was minus 3, and 2 into rotation factor of CD we got was minus 0.1535. Minus 0.1535. And M dash 21 is nothing but rotation factor of DC. So there is no rotation factor for rotation factor for DC. So keep it as 0. So add these three, it will come out as minus 3.30 kilonewton meter. Similarly for member DC, fixed end moment we got was 3, and 2 into rotation factor of DC. DC, there is no rotation factor for DC, so keep it as 0. And for M dash 21 is nothing but rotation factor of CD. So rotation factor of CD we got was minus 0.1535. Minus 0.1535. So now add these three, it will come out as 2.84 kilonewton meter. So this is how we calculate the final moment. So these all are values, nothing but our final moment. So I hope you all are understood. So our fourth step is completed here. Next we'll go for the diagram of bending moment diagram. So by using these values we'll draw the net bending moment diagram. Now we'll see. So I have already drawn the pre-body diagram of the bending moment. So span AB is carrying the point load which is not present at the center. For that it will come, the diagram will come like this triangle. I will show you. See here, the load is not acting at the center. So our pre-body diagram will come like this. So I have drawn here. So here for BC is carrying the point load. So for point load, our pre-body diagram will be triangle. So here CD is carrying the UDL. For UDL it will be parabola. Now to find out this maximum height of this, we have the formula. So we have the formula WAB divided by L. So WAB divided by L. So I have written all the values. So by simplifying, the maximum height will come out as 6. For point load, we have the formula to find out this maximum height is WL divided by 4. So I have written here. So substitute all the value, it will come out as 7.5. Similarly for this parabola UDL, we have to find out this maximum height. We have the formula WL square divided by 8. So substitute all the value, it will come out as 4.5. So now we'll go for this is our pre-body diagram. Now we'll go for the net bending moment diagram. See here, our AB value, MAB value we got was minus 1.60. So here first point is A, no, for MAB the first point is A means it comes on. So at point A, our value we got was minus 1.60. So at point A, the negative value is coming above the neutral axis. So it means it comes here minus 1.6. It comes here. For MBA we got the value 4.2. So at first point is B, no, it comes at point B. On point B it comes 4.2. See here at point B the positive value is coming above the neutral axis. So our 4.2 value comes here. Similarly for BC, the first point is B, it comes also on point B. On point B the value is minus 4.2 means it will also comes here. Both will get coincide with each other. At point B, so negative value is above the neutral axis. So it is coming here also. So at point C, now for CB, so MCB value we got was 3.3. So your first value is C, no, first point is C, no, it comes on point C, the value is 3.3. So at point C, positive value is coming above the neutral axis. So we got 3.3 means it comes here. Similarly for CD member, MCD, the value is minus 3.3. It also at point C, negative value is coming above the neutral axis. It also comes here. And finally for member CD, MDC. MDC, the value is 2.8. Here first point is D, it comes on point D, 2.84. So 2.8, the positive value is also comes above the neutral axis. So 2.8, it comes here 2.8. So now join all the lines. So here our problem ends. I hope you all are understood this Kani's method. So if you like the video, like it, share it and subscribe for the more videos. Thank you for watching.